All right. Welcome to the ASEG Webinar series. I think everyone's had a chance to log on. My name's Mark Lackey and I'm your host. Now, I was reading the Zoom etiquette and it says I should remember that it's good evening to everyone on the East Coast, but it's good afternoon to everyone on the West Coast and South Australia. And depending on where you are on planet Earth, it's hello. And if you're tuning in at 3 AM, thank you very much. I'm going to run through a little bit of our housekeeping and then I'll introduce Claire, our speaker for the evening. First of all, a thank you to our corporate members. We value our corporate members: High Size, Total Size, Bell Size, Archimedes are the corporate members, GDD Instrumentation, Santos, SAE Exploration, Southern Geoscience. I thought I'd kind of mention two things. One, from the academic side of things, is the top three certainly supply money towards the Research Foundation, which allows projects for students to go ahead. And from an academic side of things, that's quite good. It trains the next generation of geophysicists. And the other one is they allow the webinar series to occur. Part of the funding goes towards the general running and they contribute to the webinar series, which I've been thoroughly enjoying. At a more local scale, there are our branch sponsors. This is specifically a New South Wales kind of branch meeting. Claire was originally going to talk to a live audience in the same room as her, but not tonight. But I'd like to acknowledge GBG Australia for sponsoring our meetings this year, and will turn out to be next year. In regards to Zoom, if you'd like to ask a question, the Q&A link will allow you to type a question in at any stage during the presentation, and Claire and I will run through the questions at the end. Depending on the system, it either appears at the top or the bottom, depending on where it is. But the Q&A is, if you change your mind, let me know. I might figure out you've changed your mind with the question. All questions welcome. Upcoming webinars, 25th of June, 7th of July, 14th of July, 15th of July. Quite a few. I can see many Zoom meetings coming and a variety of topics, seismics, EM, mentoring, and even computations. I kindly point out some of the member benefits. Now, I highlighted two in red. This is the one because I'm editor of Exploration Geophysics, but you get free access to the scientific journal. More importantly, you get free copy of preview, what's up to date, what's going on in the industry. Both quite valued things. And this is the one I quite like. It's the networking. At the moment, we're in a Zoom meeting, but when we're allowed to be in the same room as other people, it's the networking with your colleagues and the conference networking that I find most useful. Keep in touch. There are monthly email newsletters. There's our website. I'm going with Facebook, I'm going with Twitter, I'm going with LinkedIn. These videos are all taped and they appear in the ASEG videos, so there's a good backlog now, but stay in touch with the other people. Now, I thought I should say a few words about our speaker, who's kindly agreed to give the presentation tonight. But there you go, I'm touching the wrong thing. But Claire completed a PhD in 2017. I'm hoping she did a PhD in Sydney. She'll correct me if I'm wrong. And now she's a postdoctoral research associate in the Earthbite group, I assume Deep Mars group in the School of Geosciences. And Claire leads the global stream on the Basin Genesis Hub project, funded by ARC and various industry partners. Tonight, she's kindly agreed to talk about coupling, surface evolution, and mantle dynamics with a variety of examples. All right, I trust you'll enjoy the talk. I will stop sharing and get off the screen and I'll leave it up to Claire. All yours, Claire.
Okay, so thank you, everyone. Actually, I did my PhD in France. I'm sorry. So as you can hear, I'm super French. Okay, so let's start. Okay, so thank you very much for the presentation. I would like to, let me remove that one. I would like to start to not, it's not that I really enjoy talking about myself, just that my cursus is basically the reflect of the research that I'm doing these days. So I started by doing some masters and internship, etc. I was really interested about structural geology and sedimentology. So I focused my study, my early stage of my scientific life as a field geologist. Oh, and it doesn't work. Yeah. And then I was more, I started to be more interested about plate tectonics. So I had the idea to do a PhD in Mantle, about Mantle convection models. And so I played with this virtual planet. I don't know if you're used to see this kind of model. So we basically try to approach the dynamic that we have in the mantle, but also the dynamic that we have at the surface of the Earth. So I published my first paper in Nature. So it was quite cool, a good experience. And so basically what I will show you now is the results of these two types of fields. So more geological field and more modeling field. And the result of that is the fact that we are able to couple different types of models, so surface evolution model, as well as thermomechanical model and plate reconstruction and mantle convection models. So all the work that I will show you is a part of the Basin Genesis Hub, led by Dietmar Müller, and we have different stream. We have more applied stream of the Papua New Guinea stream, the Australian Northwest Shelf stream, and I'm leading the global stream. So I will show you different manner that we that we created to couple the surface evolution and the mantle dynamic. I will especially focus on two different examples. So yeah, we started to do that because we really wanted to investigate the effect of the tectonic, including dim mantle flow and eustatic sea level fluctuation on the landscape devolution of different margins around the world. And you know that the actual topography is the result of different deformation processes. And the issue is that all these different deformations doesn't occur at the same scale. So here, for example, it's a model, mantle convection model that I did during my PhD. And it's a viscous model. So we are dealing with viscous fluids to be able to replicate the mantle convection that we have on Earth. So even if at the surface in white here, you have the plate tectonics, in blue here, you have the subduction, the slabs, in pink here, you have the continents, and the hotspot in red. So it replicates the dynamic of the mantle, but on the surface, it's way more difficult. We need to apply a yield stress to be able to simulate the deformation, to have a pseudo-brittle deformation. So basically what I will show you is really, it's really not simple because we need to link different time scale and different spatial scales. And of course, depending on the time scale we are looking at, the motion of plates, they don't have the same velocities than the motion of sediments, they don't have the same velocity of than the motion in the mantle, etc., etc. For the rheology, for the grain size. So we need to deal with multi-scale, so we need to deal with multi-physics. And of course, when we need to deal with multi-physics, there are a lot of limitations. So yeah, I think I spent 50% of my time being like this panda here, trying to deal with that. So the first issue we have is the computational resources. But thanks to the NCI, we have enough calculation time to do all the models and the debugging thing that we need to do. But one of the biggest issues is also the physics simplicity of our model. I will show you two different types of coupling, and you will see that with one of them, we can't really do numerical we can't really do simulation. We can do experiments, but not really do simulations for now. And so, of course, we need to do a lot of approximation of the rheology of the lithosphere and of the rheology of the mantle. And of course, it impacts the surface processes. So we need to be super aware of our boundary condition, to be super aware of how it will impact the surface of our model. But in the same time, we know that we need to take the entire system into account if we want to better predict the basin evolution. So different scale means different equation, and of course it means different grids too. So for the first coupling that I will show you, I will use thermomechanical model, so with these types of grid, and a balance model with the surface grid. And for the second types of coupling model that I will show you, it's a coupling between mantle convection model and surface processes model. So it will concern this type of grids. So before to show you what we can do with this coupling, I need to explain you don't worry, I will not detail, but explain you what types of technologies we use. So in the Earthberg group, I'm sure that you all know the Earthberg group and the G-plate software. So we are kind of specialized to create virtual Earth. So the first model that you can see here is a reconstruction, as well as this one. But we can also use this reconstruction to force the surface of mantle convection models and create some virtual planet like these two ones. This one here, it's also a mantle convection model. The only difference is that the plate tectonics at the the plate tectonic at the surface of this model is self-consistent, so we don't need to force anything at the surface. We also have the surface evolution code named Badlands, and we have the thermomechanical model that we use, and we use in the Sydney group, we use Underworld. So all these technologies are open sources technology. So if you are interested, just go and read the doc. Everything is available on GitHub, or you can contact us. It's a part of our job as a researcher to, be able to communicate about the technology. So don't worry, I will not detail what we have in the code. I will not talk about equations today. Well, I said don't worry, but you're all geophysicists, so maybe you would be more happy if I would do that. But I would like to show you some application and how we can use our model to better understand the sedimentation of the margin. So the first thing I would like to show you is the tectono-sedimentary simulation that we do. So this work is done with Tristan Sal, who developed the surface evolution code, Romain Bochet, who developed the coupling, and of course, a lot of other researchers. So this part is about the first coupling, and it's a coupling between surface evolution code and lithospheric evolution code. So basically, landscape evolution model and thermomechanical model. The landscape evolution model is here, and the thermomechanical model here is below. So it's really important to be able to recreate the coupled model of a margin creation, because as you can see here, you have the sediment thickness in meter, and there is a link, an obvious link between sedimentation and margin. So there is a link that we should be able to recreate in our model. And it's one of the big, this one. Yeah. So one of the big challenges is to be able to simulate the transfer of masses which are due to the surface processes, so the erosion, the transport, and the sedimentation. and to look at their influence on the continental dynamic. So of course, it will influence a lot of different things like the isostatic rebound. As you know, the elastic lithosphere is quite thin along the margin. So of course, the flexure of the lithosphere will vary a lot, as well as the perturbation of the geotherm. We will see change in gravitational potential energy, change in stress fields, etc., etc. So the erosion and the climate are both influenced by the topography, but there is a dynamic feedback between what happened at the surface and the lithospheric deformation that we can see below. So we use Underworld, initially developed at the University of Melbourne by Louis Moretti, which is now in Canberra, and Badlands developed in Sydney. And we have a two-way coupling between these two different codes. The second method I will show you, it's a one-way coupling. So before to continue, I would like to make just briefly talk about the simulations versus the experiment. For this first coupling method, we will not talk about simulations. So I know that we can criticize our model and we are quite aware about that, but the models I will show you are not simulation, they are experiments. And especially for this type of coupling models, two-way coupling model, well, we are a little bit like this rhino, okay? We have the Earth, but I mean, we know that we will not be able to achieve and to be able to recreate the Earth. We know that our models are just models. So we know the limitations of our models. Anyway, it's all right. We can use both codes to generate the models that you can see below. So what is really important in Badlands is we have the fluvial incision, we have the mass wasting, sedimentation, glacial interactions, we have carbonate platform production, for example. So Tristan had a lot of different modules here, and all these modules have an impact on the tectonic. So you have a transverse surface advection, and the tectonic, again, it's a thermomechanical model created with Underworld, which allow to model the crystal thickening, the static uplift, and the deformation that we have. And of course, this tectonic will influence the erosion, etc., etc. So to show you, I would like to briefly show you different models. So we are now able to do pull-apart models. So here it's at time 0, and here's after 2 million years. It's quite exciting because with Badlands, we are able to register to record the stratigraphy and to look at the evolution of the sedimentation in the pull-apart basin. And you can see, the development of the drainage system here, which is quite impressive. So you can follow the sedimentation and the development of the fault as well as the drainage reorganization through time. We have also collisional models, which have been done by, I think, Romain Baucher and students from Norway, or I can't remember. And today I will focus on two different types of model: extensional model, the continental margin model that you can see here. So I'm focusing on these types of model where we look at the migration of the deformation through time, and the reef model. And same thing, I also look at the influence of the sedimentation on the margin of oblique rift. Okay, so let's start. Why should we use these couple models? Because it's super time consuming in terms of calculation time. This model contains a lot of limitations, approximation of the rheology, etc. Well, I will show you that there is a strong influence of the sedimentation on the migration of the deformation along the margin. So here you have three different types of model. Okay, it's continental margin models. The first one here, you can see the one thermomechanical model. Here you have the different material field, and here it's the plastic strain. This model is not a coupled model. It doesn't contain a surface process model at the top. These two ones here contains Badlands. Okay, so you have a two-way coupling between underworld and Badlands, which is the surface evolution code. Here you have a high erodibility, which means that you will increase the sediment load. And here you have a low erodibility, so you will not have a lot of sediment here on the margin. And when you look at the plastic strain, you can see that, well, basically, yes, there is a difference in terms of deformation, and so you don't have the same fault at the same area. And so the issue here is that the boundaries of your model completely change the evolution of the deformation in your model. So we need to be super careful each time to deal with the boundary condition when we deal with the boundary condition of our model. So here it's exactly the same model, but an extended model, same thing without sediment, with a high erodibility rate and with a lower erodibility rate. And when you look at the evolution, the stress field, the plastic strain field, you can see that we have a differential deformation. So, here it's just a map at 9 kilometer depth. So here you have the map of the stress field. Here you have the same map at 9 kilometer depth, but for the plastic strain. And here it's a cross section showing the strain rate field. And what you can see is here the stress is way more important when you have a model which doesn't contain the surface processes at the surface, because of course the topography is higher, so the load is more important. And of course it decreases here if you erodate more or less. And in terms of strain rate, here you can see the fault, and the deformation will not be the same. Here you can see that you have a lot of, you have 6 second faults here, when here you have like 2 major, 1, 2, 3, 4 major faults, when here you have a differential deformation, maybe a little bit more heterogeneous. So here, if we compare the evolution now of the deformation, what we can see, so here, here same thing, you have only the thermomechanical model, and here the thermomechanical model coupled with Badlands. You can see the topography here, and here the erosion and deposition. So erosion is in green, and the deposition is in red. Here you have the plastic strain evolution. You have the you have the MO here, in red. And when you look at the evolution of the plastic strain through time, you can see that after a certain amount of time, okay, let me just replay everything. Yeah, okay, good, here. So at the beginning, the deformation, I mean, it looks like the deformation is the same, but when you increase the thickening, you can see that the deformation changed completely. And so the number of faults is not the same, and the timing of migration is not the same. So the topography and the load of sediment allow the localization of the deformation on the margin. And of course, it induces different timing of fault migration. So when you have some sediments, you have smallest faults, and the migration is slower. now, if we look at the influence of the sedimentation, so we know that we need to take the sedimentation into account when we are looking at the a continental margin setting up. And I don't know if you saw this, well, I'm quite sure you saw this paper from Sasha Brun, who showed that basically before we considered that the rifts were not very oblique, but now we know that the oblique rifts are the rule and not the exception. So here you have a G-plates model and you have different angle of obliquity, and you will see the opening of the Atlantic. Oh, maybe I can advance. Yeah, here a little bit. And so you can see that you have, during the opening here, you have different obliquities. And what we tried to understand is, the first question is, can we see the different phases of rifting in the sedimentation record? And does the sedimentation, and we also wanted to know if the sedimentation was different depending on the obliquity angle. So here you have the surface of a coupled model. What you can see is the erosion and the deposition. So the eroded area are in green and the sedimentation is in red. Here you have a cross section here of the different types of environment, depositional environment. And yeah, so we basically want to see if we can define soft timing, where is this deposition come from, etc., etc. So of course, with the thermomechanical model here, we can look at the different phases of rifting. So here you have the cross-section view, and here you have the surface view of the model. Of course, you have a huge vertical exaggeration, about 40. And so you can see the setting up of the surface and of the deformation in the lithosphere, in the crust. So we can do some source-to-thing study using this model. And so here it's another view of the coupled model. And you can see that you have an initial phase, okay. And then you have a narrowing and a subsidence, rapid subsidence. And then you have the relaxation post-breakup. So it looks like, in terms of depositional environment, we should be able to see some link between the different rift event and the sedimentation. In terms of discharge rate, it's exactly the same thing. We can easily make some correlation between the high discharge rate when we have a distributed faulting at the beginning, and then this discharge rate decrease and increase again after the breakup of the lithosphere. So in terms of depositional environment now, if you do a cross section here and you just check what types of environment you will have through time, you have this, it's a little bit like a Wheeler diagram, but basically you can see the evolution of the different types of environment through time. And you can see that during the early phase of the rift, the environment are not really deep environment. So the deep environment here are quite reduced. When after the second generation of the fault here, the environment are way deeper. And of course, after the breakup, you don't have a lot of narrow environment. You can still see this, the main episode in terms of crustal deformation and eustatic changement. And what is really interesting now is to look at the difference between the eastern versus the western margin. Because previously here, I showed you this was an average of the depositional environment through time. But you can see here that the deposition are not the same on both margin. So here you have the eastern margin, and here you have the western margin. So you can see that this sedimentation is way less important here. And on the eastern margin, you have more deep environment. On the western margin, you have more shallow environment. And so if we do a cross section here to have another view of this depositional pattern, you can see that for the cross section HP prime here, so the western margin, the environments are way less deep, and the connection between this environment, the connectivity between the deltaic environment is way less, is more important, but in terms of resources accumulation, for example, it's way less interesting than the cross section G prime, for example. So we can do the same study by looking at the types of deformation and of environment depending on the obliquity of the rift. So we choose, I choose different value. I work in radians. That's why, you know, it's 0, 15, almost 15 degrees and almost 35 degrees. So I checked the different types of environment before the breakup, during the breakup, and after the breakup. And the first thing that you can notice is, depending on the angle of obliquity, the topography is completely different. And not sure that you can really see the different depositional environment. But so here, basically, the topography is way more important when you have less obliquity. And so you will have more deep environment when you have less obliquity. So here you have a straight rift, and here you have a rift with an obliquity around 15 degrees. And if you do some cross section here on both margin, you can check the connectivity of the environment. Ooh, basically, yeah, well, we can't really see that. But so basically, it's just the same thing that you can see on this figure and on this figure. So here, the environments are shallower, and the topography is less important than for a reef which is non-oblique. So in conclusion, for about the first coupling method, we can see that the sediments record the different phases of rift. We have different obliquities which induce different timing of breakup. I didn't show you the movies, but also different rift morphologies, such as different axis bulge, like that you can see here. Sorry, I didn't show you. So the more oblique are the rift, and the less the topography is important between, the difference of topography is important between the highest point of the margin and the lowest point of the margin. So oblique breakup generates a more proximal sedimentation on the rift margin. And both margin of an oblique reef contain a different shell erosion and sedimentation supply. And this is quite normal, because I showed you previously how the sedimentation influence the evolution of the deformation along the margin. So basically, if you do discharge, the sediment flux is a little bit different on one of both margin, which is completely normal. Well, it will, this very small difference will change through time and will induce a way more important sedimentation on one margin than on another margin. Okay, so that's for a coupling between the surface and the crust and the lithosphere. But now, if we want to look at more different scale, we need to look at this Mantle scale. We need to take the Mantle scale into account, because the model I showed you just take this small area into account. So, okay, how can we do that? can we do that? Well, here you have an example of a mantle convection model, which has been done by Decker and Facina. And you can see the Tibetan plateau here, the topography of the Tibetan plateau here in yellow. You can see the cold structure in the mantle in blue and the hot structure in red. So what we want to do is to be able to use these types of model and to combine the impact of the tectonic and the mantle on the surface. So I'm quite sure that you all know the difference between tectonic topography and dynamic topography. So, and that's something we can take into account in our group, because we are designing the reconstruction, but we are also designing the mantle convection models. So with the reconstruction, we are able to see, we are able to simulate the tectonic topography evolution, but we are also able to simulate the dynamic topography evolution thanks to our mantle convection models. So the first thing that we do is the tectonic reconstruction. So I will not detail that because you can visit the Earth by Place, the G-Plates portal, etc. And we also have the mantle convection model, the surface evolution model. So the first step is to be able to couple this reconstruction and these models, which allow us to have some estimation of the dynamic topography through time. So it's the same thing I explained you before. We take the plate reconstruction, we have mantle evolution model that we force at the surface with the velocities of the tectonic plate. We also impose the location of the trenches at the surface, and it gives us some estimation of dynamic topography. So we can use all the models that I showed you and impose this data on the landscape evolution model. So this is the second example of coupling models that I will show you. And the last one, don't worry, just that one precision, the models I showed you before are two-way coupling, but this one is just a one-way coupling. So each time we impose the mantle dynamic topography on the surface mesh of our surface evolution model. Okay, so I will give you the example of the last 40 million years in evolution of South Africa, which is an example of a simulation that we can do. But just before, I will show you that we can, using only Badlands, we can look at the expression of the mantle convection on the landscape, the drainage, and the sedimentary system. So that's that was the work of Xuesheng Ding, former PhD students of the Earthby group. And so basically what we try to do in this paper is to quantify the erosional and the depositional responses due to dynamic topography in a more consistent way. And we also wanted to know if we can extract the dynamic topography signal within the stratigraphic record, and if we could infer from stratigraphic record the direction, the amplitude, and wavelengths of the dynamic topography wave. So to do that, we did some experiment, very simple experiment. So we just took a plateau like this one. So here you have a plateau with a topography, quite normal topography here, explained here, small grid resolution, etc. And what we've done is basically to design this really simple model and impose a dynamic topography wave below. And so we discovered that, yeah, we can, looking at the impact of the dynamic topography wave on the drainage system, for example, we can say, okay, yeah, here the drainage reorganization is really, really important, and sorry, is really important. The incision rate is really important, so it corresponds to a dynamic topography wave or not. So here you can see the tilt below of the dynamic topography of the model. Ooh, sorry. Okay, it's really quick. So you have the topography at the top, and you have a cross section at the bottom showing the evolution of the topography of the model. And then we can look at the evolution of the erosion and deposition pattern through time. And we can also look at the stratigraphic record on both margins. So when we looked at this model, well, we realized that it's basically what could happen below the South African plateau. So we started to see if we could compare the sediment flux evolution that we have in our model and on South Africa. So of course we need to be really careful because the time scale is absolutely not the same, but it gives us the idea that, okay, enough experiments, maybe we should try to do some simulation and to try to simulate the sedimentation around the South African margin, and especially the sedimentation of the Orange Basin. So the main question is, can we use the models, this coupled model, to discriminate the best dynamic topography model for the South African region for the last 40 million years? Why for the last 40 million years? Because it's a first step, and basically we have different types of dynamic topography model which contain the second South African plateau uplift, or which doesn't contain this uplift. So it's really easy to be able to compare these models. So the first step is to integrate the dynamic topography model. So as I told you here, don't know what is happening here. Okay, so we can discriminate what types of dynamic topography model will allow us to have the good amount of sedimentation, the good flux of sedimentation. So we choose to compare 4 different models. The model M1, because it's a model, it's a backward-forward model using tomography to estimate the dynamic topography evolution through time. The model M2, which is an extended Boussinesq approximation model. So it's a dynamic topography model which contains a certain type of approximation and which induce higher value of dynamic topography. The model M5 here, which was the preferred model to be able to study mantle plumes. And we also tried a new dynamic topography model, which contain the same approximation than the model M2, but also contain our new deformation model. Okay, so here you have the values of the dynamic topography through time, depending on their location. So basically the dashed line here corresponds to the evolution of the dynamic topography of this dot here, and the non-dashed line are the evolution of the dynamic topography of this point here. So as I showed you, as I told you before, the 2 models with extended Boussinesq approximation, so the model M2 and the model named SAB, here have a highest value in terms of dynamic topography. Okay, that's wonderful, but before to run a model, we need to find the initial paleotopography. So we have the choice, actually. We could use the Scottish paleotopography, for example, but here we decided to build the initial topography by ourselves to obtain the paleogeography. What we did is we took the present day topography using eTopo, and we removed the difference of dynamic topography through time. And then, of course, once we have this topography, we need to remove the sediment thickness along the margins. And if we remove the sediment thickness, especially on the margin, of course, it will induce a deflection if we remove this load of sediment. We also added the deflection back. And then we need to build the forcing conditions. And of course, we need to take care of the climate change. And well, this was a little bit tricky because of course, the rainfall is absolutely not the same depending on where we are in South Africa. So I decided to design different precipitation maps using a lot of bibliography. And I also decided that it would be better to incorporate different erodibilities to account for multiple lithologies, because in South Africa, the types of the lithologies are completely different if you take the sediments here or the Lesotho Massif here. So of course, the different types of rocks, granites, volcanics, sediments, unconsolidated sediment, will not be erodicated the same way. So just to show you the first results. So result here means that's the actual topography of South Africa, and this is my first model. So the evolution of South Africa through time. And so if we wait and okay. So what you can see is, well, it looks like, you know, the topography looks quite all right. The drainage system looks quite all right too. But here, the issue with this model is that we have maybe too much sedimentation on this margin, and we didn't take the flexure into account in this first model. So we needed to add the flexure back to be able to reach and to compare our results with the sediment budgets that we can find in the bibliography. So I added the flexure in my models and all the different parameters that I showed you. And so here are the results for the 4 different dynamic topography maps. And it's really quite long. And so you can see that the dispersal patterns are completely different depending on the dynamic topography map. So here, for example, you have more sedimentation on the southern basin, but here it's localized, like quite well localized close to the Orange River. Same thing here, you have more sedimentation on the northern part of the basin. And so basically here, the main drainage system is not the Orange River anymore. So the dispersal pattern here allow us to discriminate which model would be a better model. But so the model I showed you before had a constant rainfall rate. So here you have the evolution of the sediment flux through time. So you have the values from Babi et al. And here you have the values for my 4 models. Alors, just a brief explanation. Each time that you can see this peak here, as well as this very small one, it's just a reflect of a capture. So here, if you look at this drainage evolution system, so around 28 million years, you can see that here, as you increase the topography at here you will just cut the drainage system. You will have a very quick reorganization of the drainage system, and it will be visible by this very small peak. So, and it's exactly the same one for the biggest peak. Okay, so that's great, but we can see that we have a huge climate impact on the sediment flux. Here, I'm showing you the sediment flux, but it means that I need to integrate the climate maps that I showed you before. Well, the issue is we have a lot of uncertainties if once we try to make some approximation of the climate. But anyway, I have 5 different climate events. So the 5 maps that I showed you before. And if I compare the result of my model when I have a fixed value for the rainfall and when I have rainfall maps, depending on the model, when I have rainfall maps, my drainage system is maybe less good, which could mean that, well, you know, my climate maps are not good enough. So it's this model allow me to discriminate. I thought that it would allow me to discriminate the dynamic topography scenario, but actually it also helped me to design my climate maps. So here, basically, well, the rainfall that I have on my margin is too high. So if I look at the drainage reorganization, when I use my climate map, I can see that for 2 of my model, the SAB and the model M2, the drainage pattern that I have for the South Africa and for, of course, for my Orange Basin is quite, is actually quite good. So I need to use other parameters to discriminate why my models are not the same, what are the differences, which scenario would be better. And one parameter that I wish I would be able to use a little bit more is the sediment thickness map. But as you know, these data are quite rare to find. So yeah, here the difference between the model M2 and SAB in terms of sedimentation here doesn't allow me to prefer one of my model, even if here on the model M2, I have a lot of sedimentation on the eastern margin, which shouldn't happen. So here is my preferred model, is the model SAB. Again, with you have the value of the rainfall, a fixed value, and different map through time. And if I go to the end, you can see that I can find the same dispersal pattern that I have for South Africa. So I have huge deposit here close to the Orange River, and here the sedimentation is less important. The sediment flux here are quite correct. The values are quite correct. Of course, here they are doing some package, so it's a little bit difficult to compare. Here. So in conclusion, these are preliminary results. I'm still working on that, but we can see that the dynamic topography model with extended Boussinesq approximation, so the model M2 and SAB, they better predict both the sediment fluxes and the sediment accumulation in terms of dispersal pattern. There is also an overestimation of the late uplift for the model M5 here. We can see that in the topography. And the model can be used to discriminate dynamic topography model, but also climate events. So here, I know that the next step, for example, will be to change a little bit my climate maps. So, and the next step is also to test the the dynamic topography of Musha et al. 2018, and to compare the stratigraphic record that I have on my margin, because that's a good thing with Badlands. We can record the stratigraphy through time. So I would like to see if I can really compare the seismic accumulation. Just one thing, because the last thing is the good thing with this couple method that I just showed you is this was a Cartesian code. Badlands was a Cartesian code, but Tristan Saal recently developed Gospel, which is a global scale tool, and it allows us to do the same coupling between the mantle dynamic, the climate forcing, etc., etc. Here you have the new model that it published on Twitter. That's not very common, but anyway, so this is the evolution of the paleo topography around the last 100 million years using the Scottish paleo map. So you can see that this code is quite promising because, of course, you have the evolution of topography. You also have the evolution of the erosion and deposition through time. And the best part is we can now extract the stratigraphy on the top of these global models. So if you have questions.
If you have any questions, please type them into the Q&A. I'll lead off with the first question. The Badlands software, what scales can you go? You showed quite large, but can you do quite small scale?
Yeah, sure. It depends on the resolution that you want. We can, I should remove this one. It's just sorry. Okay. So, yeah, I'm not sure that I have an example here. No. Okay, maybe yeah. So we can do regional model. I'm not sure that let me just remove that slideshow. Okay. So here's the model for the Great Barrier Reef. So it's the same thing. You can record the stratigraphy, but we had we are starting to work with a researcher in Total just to make really small scale example, so a couple of kilometers, to really finally look at the stratigraphy. It will be to, more to do some workshop or give some course about stratigraphy record.
All right, so
for the global models, for example, the scale for now it's 10 kilometers.
All right, so
the resolution, sorry.
Yeah, all right, so it works to about 10 kilometers or so.
Yeah.
Yeah. We have a question here from Janelle. How are you taking uncertainty within each kind of model into account when you're combining them into a single simulation? Is there any way to quantify the uncertainty in the results? Yeah,
so that's a very good question, and that's why I still didn't publish a paper on these models, because these couple models here, because we are still doing a large range of tests to see what because when we change the viscosity, or we can, depending on the tolerance that we used, the two different model, we have a small difference, but in terms of so it will be a couple of 100 meters, but in terms of sedimentation, 100 meters, it will change everything. So basically, the only thing that we start to do these days is to increase the resolution and decrease the tolerance rate that we have to improve the reproducibility of our model and decrease the uncertainty that we have in our thermomechanical models. But for now, we are quite bad to quantify the uncertainty that we have on that it implies on the surface, especially because we are using different methods to accommodate the Eustasy in our models. So depending on the method that we use, the topography will completely change. But we are working on that, and so we are actively working on that.
So I'll ask a second question, but is there an area on planet Earth that has enough detail for you to actually fine tune with your errors?
Well, it depends what you want, what you want to look at. You know, it's still the same thing. Honestly, for South Africa, I choose this area because they are open source seismic lines. And what I really want to be able to see is to look at the evolution of the stratigraphy on the margins. And so, yeah, that's really good for me because I can constrain my model, but in the same time, it also means that I will have some issues to define my climate around 20 million years. So we need to deal with uncertainties. The issue is when you incorporate a lot of different fields and geological data, you don't have a lot of manner to quantify the uncertainties.
All right. We received a very long question from Ian. He says, interesting talk. He's fascinated.
Ooh.
Can you see it?
Yeah, okay.
Yeah.
This is more comment on points you consider when you integrate the stratigraphic record into your models, and it will be interesting when you start to integrate your modeling with the stratigraphic record. On the western continental margin and coastal plain, oh yeah, and basin inversion of the pure orange, yeah. Probably ceasing in the Aquitanian. This would have had a significant impact on drainage modification and evolution, possibly resulting in some axial drainage along the shelf. One of the issues with the offshore stratigraphic record is the resolution of seismic data. The petroleum industry data does not have the resolution to examine the complete tertiary stratigraphy record in detail, but there is a wealth of data that has been compiled over the years in support of marine diamond exploration and marine activity, which you should consider. Thank you very much. And yeah, that's actually something I'm considering because I didn't show you that, but we can do some rock tracking, which means that once I will be a little bit happier with my climate map, I will be able to have some estimation of the provenance of my sediments, the sediments I have on the margin. And yeah, this could be useful for marine diamond exploration, for example, because I would be able to track the sediment that I have. And yeah, if it comes from the mining area or from some diamond rich area. Wow, that's quite a long comment, so it's a little bit difficult to
that's okay. Ian says he'd be happy to talk with you further on this.
Yeah, I would be really happy to talk about that, honestly. And the stratigraphic record, it's something that I didn't, well, I started to look at the stratigraphic record, but I really wanted to constrain my model first using the sediment flux and the sediment thickness and the drainage pattern. So now that I have that, I'm more confident to say, okay, now we can look at the stratigraphic record.
And Janelle says, great talk, and obviously hope with the answer. Are there any other questions for Claire? All right, I don't think so. So on behalf of the ASEG, thank you for a very interesting talk. And there's something there from Millicent who says, wonderful talk. So wonderful talk, Claire. Thank you very much.
Thank you.
Thank you
very
to all
much.
the listeners, wherever you are.